Hello everyone, welcome to this video. Today I'll talk you on a agentic AI system which we have built, right? Which is basically a goal-driven agentic AI architecture. And this architecture basically takes a natural language query, breaks it into sub goals, execute them step by step using real tools, and then synthesize a final result. At its core, basically, this goal it is a goal-driven solution which works through a multi-iteration architecture designed to give an LLM the ability to plan, act, retrieve, and remember in a structured and a repeatable loop. So, looking at the high-level structure, the solution follows a layered agentic loop orchestration through the Agent 7. Each user query enters the orchestrator layer, which runs a repeated sequence of memory read, perception, decision, action, and memory write at the end until all the goals are satisfied. So currently we have a default of 20 iteration for a standard task and 80 iteration for a larger indexing workflows. So if you look at the first stage, which is the memory read, here the basically the system checks whether it already knows something useful by the performing a vector similarity search over a persistent FAISS index, which is the Facebook AI semantic search index. If semantic retrieval does not return anything useful, it falls back to a keyword matching based solution. This allows the agent to reuse a prior knowledge before making any new external calls. The second stage is the perception. In this layer, the model decomposes the user query into ordered sub-goals and keeps a track of what is completed and what still needs to be done. A key architectural decision here is that perception operates only at the level of intent. It determines what needs to happen, but never which tool should be used. And here basically comes the decision. It is based on the current goal, memory hits, and the available list of tools. The LLM decides whether to answer directly or invoke an external MCP tool in the specific iteration. It never mixes the tool execution and final answering in the same step, which keeps the control flow clean and auditable. Finally, we had the action layer, which basically has an orchestration of the MCP tools on the MCP server. And finally, once the tools are executed and we have the result, it is written back into the memory so it can inform the subsequent iterations. So this iterative loop is what gives the system its planning and reasoning capability. So if we look at the MCP tools, we have got currently 11 tools, right? Which is web search, URL, some lookup, reading, writing the files, listing the directories, indexing the documents, and some semantic based knowledge search as well. So, and also the system enforces a strong execution boundary. All the operations are restricted to a sandbox directory, right? The path travels outside anything sandbox is blocked. This ensures the agent can create, update, and inspect files without compromising the safety. Two most important tools in this are the index document and search knowledge. The indexing tool chunks document using a sliding window, embed each chunk and stores them in the memory, plus the FAISS vector index. The search tool then supports the semantic retrieval, exact identifier lookup such as the IDs and all, right, and even status-based aggregation over index tabular data. This is what enables the RAG inside the agent loop itself. Now, memory in the connective tissues is the tissue of this architecture. The system stores the fact, preferences, tool outcomes, and scratchpad entries as a typed memory item. They are persisted across the session using the memory JSON and a FASS index file and a parallel ID mapping so that the agent can recall any prior interaction which they have encountered. Anything which is more than 4 KB as a tool outcome is saved as an artifact store. The design reinforced by the type contract every year, such concepts such as the goal, observation, tool call, decision output, memory item, and artifacts are expressed through a pydantic model, which improves the consistency, traceability, and production readiness. So this tool basically was executed on a few of the standard queries, and you can see how the iteration it has gone through, distributed it into different goals, and then have generated the solution. Now, this tool was further refined for solve a domain for a domain application for healthcare domain where the claim knowledge synthetic data was provided, right? And the data is in the claims folder. Around 60 files are there, which has synthetic claim knowns and also some dummy data. So these roughly 60 files are spread across 10 categories, including the claim creation, intake, adjudication, rework, lifecycle events, metadata, lookup dictionary, source of data, and everything. So this corpus enables the system to answer the question not just from general semantic similarity, but from grounded claim knowledge as well. It can interrupt the business terms, map the codes, inspect the schema metadata, reason across the claim level, line level, event level, record view. The corpus was specially organized to support lookups, chronology, reconstruction, explanations, and domain awareness retrieval. And once indexed, it was used by the tool. So if we look at that's how the files are, and we ran this couple of 5 6 queries uh, on this data before indexing and after indexing. So if I look at like very basic question like which field tells me whether the claim went straight through the system or touched by a person, without indexing these 60 files, I can see that we are getting a message that the information is not available in the knowledge base. And systematically, if we see for all the queries, like if I want to see the denied status of the claims across the platform, is still the information is not available, so LLM is not generating any information. For example, any specific claim related information, if I want to see, right, which is specific to the metadata and the data repository, these things are not available in the knowledge base, so it was not able to answer it. So once we do the indexing and rerun all this, right, then we could see that once we rerun everything, for example, which field tells me whether the claim went straight through or touched by a person. Basically, it understands that we are looking at a auto-adjudicated claim indicator, which is present in, claim level table or in the line level table. That's how it is interpreting now once the knowledge is ingested. Then the other query is also the claim specific query. What is the for example, how many claims were denied across the platform, so it is giving a number that okay, 6 claims were denied across the platform, and the details as well. Similarly, specific claim status of a claim, what is the status, it is going through all the events, line level details, and finally whether it was paid or not. So the final status is defined here. If any claim, why I wanted to understand what was the denial reason, it is just not fetching the denial code, but it is interpreting that denial code and summarizing how at a specific procedure level it was denied, and the reason it was the denial reason is also in the plain English, it is extracting and giving it. Then if you want to understand any process journey of the claim, it is again going through what are the different states it went through, right? And then what is the timeline across each claim, and also at line level, what happened to each of the lines for this claim. So if you see, this solution is far more just a conversational, can be used as a conversational assistant, but it is also a goal driven tool using agentic system, which with the persistent vector memory, document ingestion, structural reasoning, and domain grounded retrieval. The architecture is modular, secure, auditable, and extensible, making it suitable for enterprise scenario where explainability, persistence, and safe execution matters a lot. Thanks for your time.